Hey guys, and welcome back to another AP Physics C video. Today we're going to be doing the major derivation, that is the rotational inertia of a uniform rod about its end. This could be either end and it'll work, but this is a uniform rod, right? So yeah, let's just jump right into it. So we know that rotational inertia for objects that are not point masses is r squared. It's r squared dm. But now we need to visualize, well, what is dm, right? So let's zoom in here. So here I'm going to pick out this little segment that is x away from the 0 point on the x-axis, and we're going to call that little point dm. We're going to say that little point, sorry, that little point has dm, right? So logically, if that little point is so infinitely small, you might be thinking, well, the rotational inertia matters on the height, right? Because if this was a single point, sure, I could treat it as a point mass, but since it has height, no, this does not have height. Sure, it's a rod, but we're going to treat it like linear mass, right? So it has a linear mass density lambda. We're going to treat it as if it was just a line of mass. So that little dm, if I wanted the rotational inertia at that point, well, I know the rotational inertia of a point mass is the mass times the radius squared, which in this situation would be x. So now if I wanted to take all those little dm's summed from 0 to the length, right, it would be x squared dm. So now that we know that, I'm going to transform this integral and apply the integration bounds so we can get something a little more cohesive, something that we can understand more. So from 0 to, sorry, I should zoom out here so you guys can see everything. From 0 to L of x squared dm. Now, I know this has uniform density, so I'm going to come over here and say that the density, the line, or not, linear mass density lambda is equal to mass over length because it's uniform density, right? But lambda is also equal to dm dx, where dx is a little infinitely small change in x because this dm has a little dx that it corresponds to, right? Oops. Little dx that it corresponds to. So that uniform mass density, now I can solve for dm. So I can say lambda dx is equal to dm. So now that I know that, I'm going to sub that into my integral. I'm going to get 0 to L x squared times lambda dx is equal to the rotational inertia. Well, I'll pull out my constant, and then I'll compute the integral. So this becomes m over L, because that's what density is. This becomes x to the third over 3 from the bounds 0 to L. And now this looks a lot like something you might have seen before. Sorry, this L, the entire time I've been writing that L, it should have been that L, right? So now I'm going to get L to the third divided by 3, 0 to the third divided by 3. And now I'm going to put that to 0 because 0 to the third divided by 3 is 0. And this becomes ml, and now L to the third over 3L. And I'll just do fraction work. So L to the third divided by L is L squared. So this becomes ml squared divided by 3, or 1/3 ml squared. So you might have seen that before, but that is the actual rotational inertia of a rod about its end. So hopefully that helped. And yeah, that's all you need to know from this derivation.